I will present and discuss model-implemented fault and attack injection. They are experimental verification and validation methods. They have been under development at our department for over 10 years now. So my name is Peter Folkesson, and I work as a researcher at the Dependable Transport Unit at RISE Research Institutes of Sweden. So in values, we are looking at speeding up the safety and security validation process for model-implemented fault and attack injection. As part of this effort, we will look at methods which will improve the confidence of the validation results. For example, obtained using random sampling of the available fault and attack space. And we do this by reducing the required fault and attack space. In this case, we define the fault and attack space as consisting of the fault attack model used, the location of the fault and attack, and the point in time of the fault and attack. We investigate two techniques for this. First, we are looking at pre-injection analysis, where we analyze the target system before injecting the faults and attacks, so that we may focus the faults and attacks which are effective and the results are unknown. Then, we are also looking at post-injection. Here we perform analysis after injection in order to either predict the results of subsequent fault and attack injections or focus the fault and attack injections based on previous results. So the tool we have developed and used for model-implemented fault and attack injection is called MODIFI. This stands for Model Implemented Fault Injection Tool. Our tool targets systems developed as Simulink models, and it uses the MATLAB Simulink environment for injecting fault and attack models. And these models are also developed as Simulink models. So this technique is therefore useful for early dependability validation of software developed as models. A large number of fault and attack models are already included in the tool. For example, there is bit flip faults, models supporting sensor faults, and various attack models like replay attacks. More fault models can also easily be added by the user. There is also support for analyzing and visualizing fault and attack injection results with this tool. So these are some limitations of the method which we believe could be addressed by pre- and post-injection analysis. Regarding functionality and cost limitations, we believe that adding pre- and post-injection analysis would reduce the number of tests and could still give the same results. So in this way, we will reduce time, cost, and effort of performing the experiments. For scalability and computation limitations, they will also then be addressed. For example, if you perform exhaustive fault and attack injection, these may require intense computational resources, depending on the complexity of the target system and its environment. So by reducing the fault and attack space required, less computational resources will be needed. So in this project, we are going to apply our fault and attack injection method on at least the aerospace use case 5, the aircraft engine controller. But if it's possible to use the method in any of the other use cases of the project, we would be much interested in applying our technique on those as well. Apart from incorporating the proposed pre- and post-injection analysis in our MODIFI tool, we are also interested in combining model-implemented fault and attack injection method with other analytical verification and validation methods, which we believe would facilitate pre-injection analysis